Hey everyone, and welcome to this explainer, brought to you on behalf of Forge College. Now, in our last session, we took a really cool kind of futuristic detour into AI-assisted Solana tooling with Claude and Sendai. But today, we're pivoting back to our Ethereum fundamentals track. We are jumping right back into the EVM deep dive on execution and environment. And today's topic? It's an absolutely crucial one. We're looking at the foundational blueprints of EVM storage, specifically persistent storage structures and their layout. Think of this like we're examining a master engineer's patent diagrams, drafted out in crisp orange and dark green ink on this nice textured beige parchment, as we figure out exactly where the Ethereum virtual machine physically puts your precious data. Okay, so here's our architectural blueprint for today's explainer. We'll start with the EVM storage warehouse, then look at static slots as labeled crates. After that, we'll get into packing, or stuffing the crate, followed by dynamic pointers and hashing. Then we'll map out a real contract, and finally, wrap up with gas costs and next steps. All right, let's dive right into part one, the EVM storage warehouse.
So to really get a grip on EVM storage, it helps to build a physical mental model. I want you to literally imagine a massive, highly secure and, well, pretty expensive physical warehouse. This right here is where your smart contract's canonical state lives. Now, you might recall from our memory fundamentals that the EVM has volatile memory. Think of volatile memory like a temporary workbench. You bring out your tools, you do your math, but the absolute second the transaction is over, boom, the EVM sweeps everything off the bench straight into the trash. It's totally ephemeral. Persistent storage, though, that is our massive, permanent warehouse. It survives between transactions. It holds your token balances, your contract owners, your app's absolute truth. But because it's permanent, the EVM charges a hefty premium to store anything in there.
And the fundamental building block, the basic unit of this persistent warehouse, is what we call the storage slot. You can visualize a storage slot as a standardized, heavy-duty crate. Every single crate in this entire warehouse is exactly the same size. It holds precisely 32 bytes of data. No more, no less. If you have exactly 32 bytes, it fills the crate perfectly. But if you have less, well, we kind of have to figure out what to do with all that empty space.
Which brings us to part two, static slots labeled crates.
Okay, so how do we actually assign our data to these crates? Well, the Solidity compiler acts like a remarkably strict warehouse manager. When you declare static variables in your code, like, say, simple integers or addresses, the compiler assigns them to fixed, totally predictable crates. And guys, the sheer scale of this warehouse is mind-boggling. There are 2 to the power of 256 possible slot indices. That is essentially an infinite aisle of crates. It's a number so mathematically huge that if you just randomly picked a crate to put your data in, it's virtually impossible for anyone else to accidentally stumble upon it. So what the compiler does is it starts at slot 0 and just walks down this infinite aisle, assigning your statically declared variables to crates one by one.
Moving on to section 3, packing, or stuffing the crate. Now remember what I said about persistent storage being super expensive? We really don't want to waste space. So if we have smaller items, we use a clever technique called packing. Our strict warehouse manager, the compiler, has a very specific set of rules for this. Small variables, like a Boolean, which is just 1 byte, or an Ethereum address, which is 20 bytes, they can actually fit comfortably together inside a single 32-byte crate. But here's the catch. They literally must be declared consecutively in your source code. If you declare a Boolean, then a massive 32-byte integer, and then another Boolean, the compiler can't pack them. It's just going to put them in completely separate crates and waste all that space. When they are consecutive, the compiler packs them, starting from the low-order bytes and working its way up.
This packing trick absolutely saves us storage space, but it introduces a somewhat hilarious mechanical catch known as the read-modify-write cycle. Imagine you have a crate perfectly packed with an address, a Boolean, and a small integer. If you want to update just that one tiny Boolean, you can't just magically teleport it inside. Nope, the EVM has to drag the entire heavy crate off the shelf, pop it open, pull the contents out, carefully swap your tiny little Boolean, repack the whole crate, and seal it back up. This takes extra effort and, you guessed it, extra computational gas. So packing is amazing for space, but it makes partial updates a bit of a chore for sure.
So up to this point, we've only been talking about fixed, static variables. We know exactly how big an address is. We know exactly how big a Boolean is. But what if we don't know how big the data is? What if we have a list of users that could just grow infinitely?
That takes us to part 4, dynamic pointers and hashing. Dynamically sized data requires a completely different approach. The compiler totally changes its strategy here.
For dynamic arrays, the static slot we declared doesn't actually hold the array itself. Instead, it holds the length of the array. It basically acts like a signpost, pointing to a completely hidden aisle somewhere else in our massive warehouse where the actual items live. For mappings, which are essentially key-value dictionaries, it's more like a magically accessible keyed locker. The main slot acts as a seed, and we combine that seed with the specific key we're looking for to find the exact hidden locker.
And this brilliantly illustrates exactly how it does that. The deterministic hashing formula you're looking at is exactly how the EVM finds that hidden locker. To find a mapping entry, it takes your key, pads it out to 32 bytes, takes the declared slot position P, pads that out too, squishes them together, and runs the whole thing through the kekok256 hash function. This spits out a wildly random-looking coordinate somewhere in that vast 2 to the 256 warehouse. Because it's a cryptographic hash, it guarantees that dynamic data elements will be completely scattered across the slot space. This totally prevents collisions with our neatly organized static crates.
Okay, section 5, mapping a real contract. Let's make this concrete. Let's see how this all builds into a practical application by mapping a real Solidity contract right onto our warehouse shelves. This way, you can see exactly how the compiler executes this blueprint in practice. So we've got 7 variables declared in order here. First is total, which is a large integer. It gets its very own full crate at slot 0. Next up, we declare an owner address and a paused Boolean. Since an address is 20 bytes and a Boolean is 1 byte, the compiler cleverly packs them together right into slot 1. Nice and efficient. Then we have small a and small b, two 16-byte integers. 16 plus 16 is exactly 32 bytes, so they slide perfectly into slot 2. At slot 3, we declare items, which is a dynamic array. Remember, slot 3 just acts as the signpost, storing the array's length. The actual items themselves are hidden away starting at the hash of 3. Finally, our balances mapping is declared at slot 6, but its actual values are scattered deep in the warehouse using that kekok256 formula we just looked at. Pretty cool, right?
And finally, section 6, gas costs and next steps. Now, as an engineer or an auditor looking at these elegant technical diagrams, you might be scratching your head asking, okay, why does any of this low-level warehouse layout actually matter to me as a Web3 developer? Well, the crucial point is this. The layout directly dictates your gas costs. Packed variables are phenomenal. They save gas if you're updating them together in a single transaction, because you're only writing to one crate. But if you pack variables that you only ever update separately, you are actually wasting gas. You are forcing the EVM to perform that tedious read, modify, write cycle on the whole crate every single time. And while dynamic hashing beautifully prevents collisions in our infinite warehouse, actually calculating those kekok hashes costs computational gas. So like everything in engineering, it's a trade-off.
So now you know exactly where the crates are stored, how they're packed, and how to find all those hidden aisles. But what happens when you need to resize those dynamic structures on the fly? How do you push and pop data from those hidden arrays without completely breaking the bank on gas? Well, that is exactly what we're going to tackle in our next lesson on handling mutable dynamic data structures. Until then, to dive deeper into this subject and continue mastering your Web3 journey, be sure to check out forge.college. Thank you so much for learning with us, and we'll see you in the next explainer.